A frame of reference where Newton's first law holds good. Firing bullets, constant rate, high speed. The bodies move with variable speed is a non-inertial frame. This is essentially for the conservation of linear momentum. Picture with his relativity. And these are called variable mass problems. Hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram Pre-University, Mysuru. Before we start, as usual, thought for the day. Salute your work and you need not salute anyone. Pollute your work, then you will have to salute everyone. Commitment and sincerity are two ornaments which will make your inner sight look beautiful. Continuing my session on laws of motion, my today's discussion will typically involve examples to understand conservation of momentum and a very beautiful concept called inertial and non-inertial frame of reference. Now, recall the definition of momentum. We told it is the ability of a body to impart velocity to some another body, capacity of a body to transfer momentum to another body. And mathematically, it was defined as the product of mass and velocity. And yesterday, we beautifully established the law of conservation of momentum, where we told the total momentum, total linear momentum of an isolated system always remains constant, or the sum of final momentum of two colliding bodies in a straight line is always equal to the sum of initial momentums. Now, to substantiate and justify all these thoughts, we will understand examples to show the conservation of linear momentum. First one, a common example of recoil of the gun. You see, when a bullet is fired from a gun, as we fire a bullet from the gun, the bullet moves forward towards the target while the gun recoils or it moves backwards. A very simple example to illustrate the law of conservation of linear momentum. As a bullet is fired from a gun, typically a double-barrel gun, you see, the bullet travels forward in a direction to strike the target, but the gun moves backwards. This is because to conserve the momentum, or to see that the bullet gets momentum in the forward direction. And here, necessarily, a proper force is required to hold the gun. So you see, as the bullet is fired, the bullet travels forward in a direction to strike the target, whereas the gun moves back, justifying the law of conservation of momentum. The second example, when a machine gun mounted on a van, machine gun mounted on a van used for firing bullets at a constant rate, the van is set into motion opposite to the direction of travels of the bullet. So, I have a machine gun which is set up on the top of a van. I start firing bullets, constant rate, high speed. Now, in order to conserve linear momentum, the van moves in a direction opposite to the direction of bullets, because there the impart of velocity is happening in the direction of the bullet. So again, a proper force is required to hold the gun. You see, films related to wars, tanks, the moment the bullet is fired, the armature is fired, the vehicle moves in a direction opposite to travel of the armature. This is essentially for the conservation of linear momentum. The next one. When a body of mass m explodes into two parts of equal masses, then the two parts move with the equal speed in opposite directions. Again, a very beautiful example. This is called fragmentation of mass. A huge mass of capital M explodes into two parts of equal mass. I say the two parts, the two smaller parts, the two smaller fragments have equal mass M and M. Then the two parts should travel with the same speed, but always in opposite directions. Fragmentation of mass. Huge mass split into two smaller masses. And those two smaller masses of equal mass travel with equal speeds in opposite direction. And finally, the motion of a rocket is based on the principle of conservation of momentum. Again, a common example, when a body, or you can say a sailor from the boat jumps into the river, he moves backward, the boat moves forward. Again, a typical example for conservation of linear momentum. So we have seen examples like the recoil of the gun, the recoil of the vehicle, fragmentation of mass, launching of a rocket, which are all basic examples to illustrate something called as conservation of linear momentum. Now we will understand again a beautiful principle called principle of rocket propulsion. How actually a rocket is launched on the principle of conservation of momentum. Observe, dear students, I consider this to be a rocket. This is the head of the rocket, the center and the tail. And the fuel is always placed at the center. Rocket propellants, you call them. Head, the center body where the propellants are placed, and the tail. What happens here is there is combustion of the fuel which is placed at the center of the rocket. Here exclusively we see combustion of the fuel, burning of the rocket propellants at a very high speed, so that all the excess gases are thrown out from the tail of the rocket. All excess gas, which is the resultant of the combustion, they are thrown out from the tail of the rocket, which means the rocket will gain momentum in the opposite direction. See, very beautiful. All excess gases are coming out from the tail of the rocket, so that the rocket gains momentum in the opposite direction and it can set itself into the outer space. See how beautifully again linear momentum is getting conserved. There is combustion of the rocket propellants, the fuel, all extra gases are thrown from the tail of the rocket downwards. This happens so that the rocket gains momentum in the opposite direction and can place itself in the outer space. But again, if you observe the mechanism, there is a classical failure here. My classical physics, Newtonian mechanics is getting failed here. How? The very concept that mass is invariant doesn't hold good here. My classical mechanics told, Newtonian mechanics defined, under all conditions, mass of a system should remain constant. But here, during propulsion, during rocket launching, there is a decrease in the mass of the system. With the upward motion of the rocket, the mass of the system is getting reduced. This is called variable mass problem. Fall of a dewdrop. As a dewdrop falls down in the atmosphere, it will collect the dust particles. So, as its motion is happening downwards, its mass is increasing. Again, an example for invariance of mass. So, certainly we see examples where conservation of mass, consistency of mass is questioned during motion. And to answer that, Mr. Einstein comes into picture with his relativity. And these are called variable mass problems. Now, a very important and interesting topic to understand motion, something called inertial and non-inertial frame. First, we will try to understand an inertial frame of reference. Now, I construct a frame of reference X, Y, Z. Earlier in my discussions, I have clearly told a frame of reference is required to understand the motion of a particle. We told no, in which plane the particle is present, what is its distance from the origin. So very clearly, the motion of a particle in certain region of space is understood using a frame of reference. Now, what is this inertial frame? Definition says, any frame of reference where Newton's first law is valid, or Newton's first law holds good, is called an inertial frame of reference. A frame of reference where Newton's first law holds good. Newton's first law is valid, which means in such a frame of reference, the body should move with constant speed. And therefore, it is called non-accelerated frame. A body cannot have acceleration in an inertial frame. It should move with constant speed. Velocity of distant stars with respect to Earth, it's measured in an inertial frame. So what is inertial frame? Non-accelerated frame. Here, the motion of bodies should happen with constant speed. Or I say, Newton's first law of motion is valid. Now, a frame of reference which is accelerated, where Newton's first law is not valid, or where the bodies move with variable speed, is a non-inertial frame. Non-inertial. It is accelerated frame. Motion of bodies tend to happen with variable speed. For example, motion of the earth. So, inertial frame, no acceleration at all. Any motion happening in an inertial frame must obey Newton's first law. Body should be moving with constant speed. But non-inertial, exactly opposite. So, my dear students, in this session, we understood examples which justified the conservation of linear momentum. We understood the launching of a rocket as an example for linear momentum, through which we understand variable mass problems. And finally, the nature of motion dependent on inertial and non-inertial frames. In the next session, I come back with friction and related concepts. Until then, have a nice time. Thank you.